For the next video, we're going to cover the next two sections of the textbook, 7.4 and 7.5, because there are so many similarities between these two sections, it will actually save us time. So I'm going to call these combined as exponential functions. Okay? In the first semester, we talked about what a function was. It is something that relates our input values to our output values, such that when I give you an input, it goes to exactly one output. Well, an exponential function, well, let's talk about the type of function we've been dealing with. This is a linear function. A linear function is something that we can write as y equals mx plus b, okay, or y equals ax plus b. Okay, we use m to represent slope, but in general terms, it's anything that has a constant times a variable to the first power plus a constant. And in this case, a cannot equal 0. Okay, if a was 0, this would just be a constant, and it would no longer be a linear function. So let's talk about exponential functions. An exponential function is anything that can be written as y equals a times b to the x. Notice here the variable is in the exponent. That's why it's called an exponential function. I do have some restrictions here. Again, a cannot equal 0. Okay? This b is called the base of my exponential function. The base has to be bigger than 0, and the base cannot be equal to 1. Okay? So the base has to be bigger than 0 and not equal to 1. Some key things about this is it is a growth function. Okay? It's called an exponential growth function if b is greater than 1. It is called a decay function if 0 is less than b, which is less than 1. So if this number is more than 1, it's going to be a growth function, which means it's going to grow over time. And if the base is between 0 and 1, it's a decay function, which means it's going down over time. And we're going to see how to graph these in a little bit. Next thing I want to talk about is on our linear functions. So I'm going to make an xy table here for the linear function. And I'm going to do y equals 2x plus 3. So when x is 0, y is 3. When x is 1, I get 2 plus 3, which is 5. When x is 2, I get 4 plus 3, which is 7. And then I'll get 9. When I put 4 in, I'll get 11. Notice, as I'm going successive numbers for x, so every time I add 1 up here for x, I am adding 1. Adding 2 for my y value. You can tell if something is a linear function is if you have what is called a common difference. Okay? So 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. Okay? If I'm adding the same number to get from one number to the next, that would be a linear function. Next one I want to make a table for is y equals 2 to the x. So I'm going to put the same numbers in, 0, 1, 2, 3, and 4 for my x and y. So for x, I'm putting 0, 1, 2, 3, 4. Put a 0 in here. 2 to the 0th is 1. 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. And if you notice here, going from here to here, I add 1. Going from here to here, I add 2. Then I add 4. Then I add 8. Okay, anytime that you see the pattern where you're adding the same thing that's kind of up at the diagonal from the previous one, or when you do it again, you're going to be adding this, what's up on the diagonal, you're going to realize, hey, I'm actually multiplying, okay? And the way I find out what I'm multiplying by is I'm going to take the right-hand number divided by the left-hand number. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So anytime you are multiplying by the same number, that's how you recognize something is an exponential function. And you can check that from a data table. Okay? What we're going to now look at is there are other ways to write this exponential function where this b looks a little bit different. Remember, this b is a number. It's not a variable. Okay? So what we're going to do is we're going to remember, hey, if b is greater than 1, it's a growth. And if b is between 0 and 1, it's a decay. And an exponential model so this is like for a real-world situation. Number of bacteria on your sponge goes up a certain percentage every couple hours. How do we model that? Okay, and that exponential model, there's two of them. One of them is on page 460. It shows you the growth model. And then on 472, it shows you the decay model. But I'm going to write them as a single model. Okay, y equals a. 1 plus or minus r to the t. Okay, if I'm using a plus r, it's a growth model. If I'm adding a number to 1, I'm going to get a number bigger than 1, which means it's a growth. If I use minus r, that was going to be a decay model. Okay, each one of these things has different terminology. This a is the initial amount. This whole thing that's inside the parentheses is called the growth factor or the decay factor. So this would be the growth / decay factor. T stands for time. And that time needs to be the same units of time as your rate. And this r by itself is either the growth or decay rate. And this has to be a decimal. So if it's a percentage, you are going to change it. So how does this work? Well, let's say that I purchased a car for $5,000. And it loses value at 8% per year. I want to know what my car's value is going to be after 5 years. So all I'm going to do is I'm going to stick these numbers into this equation. My initial amount is $5,000. I'm going to write the 1. I'm losing about amount, so it's decay, so I'm going to put a subtraction. 8% is 0.08. And the number of years is 5. Okay? I'm going to do the 1 minus 0.08, so I get 5,000 times 0.92 to the 5th. And I stick that into the calculator so I get 5,000 times 0.92. And again, to raise something to more than a squared power, you're going to use that caret symbol to the 5th. And it says that it's going to be worth approximately $3,295.41. Okay? You should be able to look at the different parts of an exponential function and tell me what the initial value is. Tell me whether it's increasing or decreasing, whether it's a growth or decay function. Be able to tell me what its growth rate is or its decay rate is, what its growth factor or decay factor is. Okay? So next thing I'm going to do is I'm going to show you what we're going to do to graph exponential functions. And we're not necessarily going to graph these that are dealing with money types of things. We're just going to graph the base exponential functions. Okay, so I'm going to pause the video and then get to the graphs. I'm going to graph 3 exponential growth functions. Okay, the first one is y equals 2 to the x. The second one is y equals 3 times 2 to the x. And the last one is y equals negative 2 times 2 to the x. One thing I want to warn you about where students mess this up. Some students rewrite this as 6 to the x. I cannot do that because of order of operations. Exponents happen first, so I have to raise the 2 to the power and then multiply that answer by 3. Okay. When you are graphing an exponential function where it's just like an integer to a power or a small fraction to a power, not one of our models, you will always put the numbers that make your exponent, in this case just x, negative 2, negative 1, 0, 1, and 2. So what we're going to end up doing is we are going to be graphing where x is negative 1, negative 2, 0, 1, and 2. Those will be the x values that we end up graphing. Okay, and I'm going to put some y values, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So first thing I'm going to do is for y equals 2 to the x, I want to do 2 to the negative 2, which is 1 over 2 squared, which is 1/4. So when I put a negative 2 in, I get 1/4. If I put a negative 1 in, 2 to the negative 1 is equal to 1 over 2 to the first, which is just 1/2. 2 to the 0th is 1. 2 to the first is 2. And 2 squared is 4. This would be the graph of y equals 2 to the x. One thing I want to point out here is this line is never going to go below 0. Because it'll never go below and it will actually never touch 0. This is called what's called an asymptote. It's a line that the graph gets very, very close to but never touches. I'm going to pause the video for a second, then continue. And for the last 2 functions I'm going to graph, I'm going to show you a shortcut to come up with the numbers that you want to graph. Okay, a lot of times when we're going to do these graphs, we're going to have the base function, and then we're going to do something to that base function. Okay? Well, this says, hey, we'll do this one first. We'll put the 0 in. It says, put a 0 in for x. 2 to the 0th is 1, and then take that 1 times 3, and you get 3. Okay? Let's put a 1 in. Well, it's 2 to the first, which is 2. 2 times 3 is 6. Okay? Instead of re-putting all those numbers in for your exponents, if you know what the base function is, the 2 to the x function, whatever you have out in front that you're multiplying by, just take the answer from your base function and multiply it by that number. So 3 times 2 to the negative 2 would be 3 times the 1/4, or 3/4. 3 times 2 to the negative 1 would be 3 times 1/2, which is 3/2. And down here, I'd get 3 times 4, which is 12. So at negative 2, I get 3/4. At negative 1, I get 3/2, which is 1 1/2. At 0, I get 3. At 1, I get 6. And at 2, I get 12. And the last one. Similarly, I'm going to take my 2 to the x value and multiply it by what's out in front. So I'm going to take negative 2 times 1/4, which is negative 2 over 4, which is negative 1/2. Negative 2 times 1/2 is negative 2/2, or negative 1. Negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. Negative 2 times 4 is negative 8. So at negative 2, I have negative 1/2. Negative 1, I have negative 1. At 0, I have negative 2. At 1, I have negative 4. And at 2, I have negative 8. And that would be this graph. So there are some things that I want to point out based off of these graphs. If your a is greater than 0, my growth function goes uphill like this. Okay? That's these first two, the orange and the red one. If the a is less than 0, we are going to flip the graph across the x-axis. So it's going to actually look like that. That's just an upside down growth function. This is still a growth function, but it's just reflected. Other things I want to point out. Notice that the y-intercept for the first one is 1. Well, what number do I have in front here? I have a 1 times 2 to the x. For the second one, it's 3. I have 3 times 2 to the x. For the last one, I have negative 2. Negative 2 times 2 to the x. So if I have y equals ab to the x, where this exponent is just an x, okay? Not like an x plus 1. If it's just an x, this a right here is your y-intercept. Okay? And then let's take two numbers. We'll take the 1 value and the 0 value. So I'm going to take f of 1 over f of 0. So for the orange one, f of 1 is what the y value is at 1, which would be 2. F of 0 is 1. 2 over 1 is 2. F of 1 over f of 0 gets me my b value. That's the b value. Okay, and again, that's only if the exponent is just an x, not an x plus 1 or whatever. So let's try it with the red one. F of 1 is 6. F of 0 is 3. 6 over 3 is 2. F of 1 is negative 4. F of 0 is negative 2. And again, I get 2. So this is a way that if you're given a graph, you can actually come up with the numbers for your thing, for your function. Okay, for a decay function graphing, it's going to be similar, but instead of graphing like y equals 2 to the x, what we're going to end up graphing now is y equals 1/2 to the x. We're going to turn these all into decay functions. I'm going to use the same multipliers. 3 times 1/2 to the x, and y equals negative 2 times 1/2 to the x. Refill out my data table. And what you're going to see is that I end up with pretty much the same numbers. They're just in a different location. Okay, so first one is y equals 1/2 to the x. So that's 1/2 to the negative 2. Flip it over and change the sign, which is 2 squared, which is 4. This is 1/2 to the negative 1. Flip it over, change the sign, that's 2. Any number but 0 to the 0th is 1. 1/2 to the first is just 1/2. And 1/2 squared would be the 1 squared over 2 squared, which is 1/4. So if I put a negative 2 in, I got 4. And I'm going to do these in blue. If I put a negative 1 in, I had 2. If I put a 0 in, I had 1. I put a 1 in, I get 1/2. Put a 2 in, I get 1/4. So that would be this graph. Notice this is the exact same graph as y equals 2 to the x, except this one's reflected across the y-axis. I'm going to do the same shortcuts I did before. I'm just going to take this value and multiply by the number in front. 4 times 3 is 12. 2 times 3 is 6. 1 times 3 is 3. Then 3/2 and 3/4. And again, you should note that I have the exact same values I had for y equals 2 to the x, except I'm reflected across the y-axis. So I end up with 12. So 4, 5, 6, 7, 8, 9, 10, 11, 12. 6, 3, 3/2, 3/4. And for the last one, I'm going to do negative 2 times 1/2 to the x. Negative 2 times 4 is negative 8. Negative 2 times 2 is negative 4. Negative 2 times 1 is negative 2. Negative 2 times 1/2 is negative 1. Negative 2 times 1/4 is negative 1/2. So I'm going to go negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 8. Negative 4. Negative 2. Negative 1. Negative 1/2. So our exponential decays. If a is positive, the graph looks like this. And if a is negative, our graph looks like that. So those are 2 more memorized shapes of graphs that you're going to have to know. You already should know the linear function, which is a straight line. Okay, all lines are straight, but it's a straight non-vertical line, and a non-horizontal if it's going to be a linear function. And then we have our exponential growth and exponential decay. So using this information, you should be able to do the practice problems that I'm going to give you and then be able to work on the problems over the next couple days in class.